option juga mau. So let's wait for 10 minutes, 5 minutes and we start. Yeah, so yeah, very good stuff. I don't think so a lot of people will be joining today. Am I audible? Okay, so before moving to the assignments, what I thought for today was to let's start with the concepts of linear regression, etc. Applying linear regression and all to using this Python libraries. Till now, what you have seen is very much reduced form of like small version of non-scale version of linear regression, using some random number of weights and training it manually by writing the code. But that's not the case with Python. Okay, so when that's not the case with libraries, so libraries help you ease the task. So today we will discuss linear regression as well as logistic regression, both of these things together. And then what we can do is, well, let's see if time permits, we can discuss the assignments. Well, I mean, time will permit, obviously. Is the screen visible? So there are basically 4 to 5 libraries which are required to implement machine learning. First one is NumPy, the other one is Pandas, next one is Scikit-learn. And we will write all this with more libraries coming in. Okay. So yeah, what is linear regression? You are given some x1 feature, x2 feature, and you are asked to predict y. Correct? So scikit-learn, let's import scikit-learn. It's not implemented. This is written as scikit-learn is written as sklearn. Yeah, so this one is for logistic regression. Let's do linear regression. Okay, so let's load Boston dataset. So Boston dataset can be loaded like this. So what we do is load this function, and then this Boston dataset comes like this. Okay, so let me show you. So yeah, this dataset collection had some bias problem. Okay. So that's why you can fetch the dataset from this source. That's the code they have done. Alternatively, you can use this fetch California housing dataset. So let's used this. It has been a long time since I used this data set, so since then there have been a lot of changes. Okay. So this is house data set. So let's print this housing data set. Okay, so you see a lot of features here, a lot of stuff. Okay, so this data set, as you can see, feature names are median, whatever it is, median house value, target name is house value. This is house age, average bedrooms, average bedroom, population of this area, latitude, longitude of the area, etc., etc. There are a lot of features in this data set. Okay, so what let's do, let's convert this data set to something variable. Okay, so to convert this data set to some variable format, let's import pandas. Okay, so housing is equals to housing like this now. So yeah, housing data looks like this. Okay, so these are the values, and let's set the target value as well. So we didn't set the target value. So target is equals to td dot, sorry, what was that? Housing data dot target. Yeah, so housing data had some initial variable named target. I can just okay. So now this housing data looks like this. It has some target value. Okay. So yeah, as you can see, these are latitude, longitude values. They are California. All houses are situated in California only. So let's deal with some basic features such as median house age, average bedrooms, population, average occupation. Let's remove latitudes and longitudes. Okay. What is the function for the columns? So from housing we drop here. So these are all this is new data set. Okay, so yeah, am I audible? Are you able to hear me? I'm going very slowly so that those people don't get confused. So till now what I have done is I have looked at the data set. I have removed latitude and longitude because those are geographic data, and handling them makes it difficult for beginners. So right now we have x1, x2, x3, x4, x5 and x6 and y. Okay. So our model should look like x0, sorry, w0, what is bias, plus w1 x1 plus w2 x2 till w7 x7 equals to y. This is what linear regression is. Okay. So okay, by the way, this Gemini also gives recommended plot feature. So if I run it, I'm just showing you. So it will generate recommended plots for these charts. So these are very good for exploratory data analysis. So if you take a proper data visualization or data analysis course, they will teach you there this also. Okay. So as you can see, it's running. So they are basically histogram plots showing number of data points, number of data points, and XY scatter plots also. These are 2D plots. These are 1D plots. Okay. So if I open this plot, so as you can see, frequency of this has converted this raw data into buckets. Med.Inc is not numerical data. I mean, it's a numerical data. It's not an integer data, so it has converted to buckets. So as you can see, Med.Inc is around 4,000 rows. Out of 20,000 rows, 4,000 rows, 3,500, and 3,500. So this is around 7,000, 11,000 out of 20,000 rows lie between 2 and 4. Okay, 2 and 4.5, whatever it is. So this means these are the maximum values in it. And so if we open 2.5, somewhere 2.5 or something. So for 2.3, 2.5, you can see the values are near to 0.7, 0.89. The values are not high. So this is median income, I think. So this suggests that median income of the area is very low. I mean, this is compared to this, like for this income, they have small houses and they have low price houses. You can also see here. 2.3 is median income. Okay, for that the price is 0.89. For this 2.5, this price is 0.77. So as you can see, this poor person is living in a expensive house and this rich person is living in a comparatively cheap house. Okay. So yeah, these are the plots, and this is how you can interpret these plots, and these are very good at generating visualizations and the reports for your projects. Okay. These reports are mandatory because people working in non-tech, where you have to show a machine learning model, you have to take out, they will not be able to understand what type of data have you used. So this is how you can show. So house age, so as you can see, this house age plot is very scattered, it doesn't matter. Like house age, somewhat different types of aged houses are there. Okay, so this one is good. This is showing okay, it's not. It is average bedrooms versus average cookie. Yeah. So obviously, the more number of bedrooms, the more number of rooms. So this doesn't make any sense. Yeah, this one looks nice. It shows what is average bedrooms versus population. Okay. So I don't know how they have drawn this plot, which is scatter plot. So I think this is symmetric around this axis. Okay. So anyways, I don't know. These are some random plots generated by the AI model, and they are of no use to us. I mean, some of them might be, some of them might not be. So this is a simple code written by Gemini AI. So I'm creating this. Okay. This is how you can generate. If I write generate code using housing, so it will basically give me this data frame, and I suggest it to draw a plot, and it will draw a plot for me. Okay. They will practice data file open. So it basically opens a new collab sheet from here only. Okay. Google sheet in which this data is present. So yeah, these are really nice features. So if I go like this, you see, I'll show you. So if I allow it, so it will open a sheet for me. With all these data values and you can use this data. So it has given me the link. If I click on this link, it will open the link for me. And it has given me all the 20,000 rows here. Let me show you by going down. It has 20,641 rows. So now your whole data has been exported from that Python library to this Excel sheet. And now you can also draw the same plots here. Okay, so consider it, let me show you. So if I take median income versus target, this column and this column, and I insert a chart. Okay, so this chart is column chart. Let's make it a line chart type of. Let's make something sort of. Scatter chart. So yeah, as you can see, this whole thing somewhat shifts upwards with median income or median increment. Okay. So yeah, that's how you can draw these charts here as well. Okay. Till now there should not be any doubts. If there are, just let me know. Okay, so now let's, this data is very simple. I will show you how to build a model without normalizing the data and with normalizing the data. Okay, so let me just write the code. Let me first split the data into train, validation and test sets. Okay. This is mandatory because otherwise we will not be able to identify whether the data has overfit or not. Okay. So let me just calculate this. It imports train test split from scikit-learn model selection package, and it splits 20% of data from between train and test this thing, and then train data is further split into this shape, into test, into validation and train. Okay. So now this data set has been split in three different data sets. Okay. So now let's basically use this data to train a linear regression model. Okay, so yeah, this has a lot of stuff here, and I'll show you. Pasting it here. So as you can see, scikit-learn have this package to use linear regression model. Okay, so now what we will do is we will prepare this data into three different data sets. We will take target. We will basically take train data and from the target variable, then train x-train. This is x1 to x7. We draw the target variable. We do it for all three data sets. Okay. Then we define a linear regression model. Okay, and then we fit this data here. It has fitted. Now we predict the values. These are from validation data. Okay. So let me just write it as whole here. Okay. And it will show me the mean square error. So mean square error on validation is this much, and on train test is this much, which is quite high comparing. See, this is square of this thing. Okay. So I mean the decimals, the error, if I say so, if I say what is square root of 0.6? Square root of 0.6. What is 0.77? Okay. It is showing me the error is 0.77 around that. Okay. Why? So consider this is 0.17 and I give it so output predicted by this model is 1.7 or 7.4. Okay, so this is just double of that, but the error will be 0.7. This means that output predicted for these low houses is quite high. But for these values, where the medium income is very high, okay, the output predicted is, the error is quite low. So we cannot compare, we cannot completely say that, okay, that if this error is manageable or not. So what we do is, this is very simple thing. But since we don't know, like we are using bias or we are using regularization, etc., etc. So let me just write this code again and ask it to basically even hyperparameters of linear regression model. Okay. So it will be in hyperparameters linear regression model. So intercepts can be positive and negative. Okay. So either it has to true or false. Okay. So this is the only hyperparameter in linear regression. So we can about it. Okay, so yeah, this is what I was searching for. The other code is very simple. Other code, say it uses for loop, etc., etc. But there's another package which basically constructs a grid of parameters. So you have two possible values of hit intercept, two possible values of positive. So it will create a confusion matrix type of thing, where it will place each and every value and then it will search over that value. So grid search tree performs that operation only. We pass linear regression to this grid search CV. We pass this parameter grid here. Okay. So okay. So another thing is, when using grid search CV, we do not need to basically create validation data, because it splits validation data automatically from train data. Okay. So even if I remove this line, it will automatically use this data here. Okay, so now this code is working because it was using previous validation values. So I'm leaving this code as it is here. Let me run it here. print best model. Okay. So grid search was fit on this data and it is not giving any best estimator here. So I think both of the values are true only. Okay. So yeah, I think this is the best model. And yeah, this grid search. Sorry guys, my internet. Am I audible? Okay. So what I was saying is, see, this has given fit intercept true, positive true. That's why the values are not inside it, because they are false and yeah, true and true. So because these are default values, and for these values the initial loss and updated loss, etc., everything looks same. Okay. So yeah, this means this was already the best model for this data set. So this is how you do linear regression. Got it? This is a very basic step. You just take the original data, split it. Now the problem is this data has not been scaled. So scale this data. Obviously normalize this data. And then find best parameter and train the model. Okay, so till now we have imported these means for error packages, etc. We have this another package, standard scaler. Standard scaler scales the data. Okay. So we split the data. From here we copy the code. This is the updated part. So you can see here we have taken we take the possible margins, maximum minimum margins of trained data only, and then we apply those margins on test and validation data. Although validation data is not needed, but we are also doing it translations as it is. Okay. So here you can see the error. It's 7461. 861. I don't know if it was reduced or not. Let's check. It's less than false. This means the error has increased only. This means the doing scalar transformation has created some havoc and it has basically increased the error. So yeah, this is what with standard scaler we can do. Okay, so yeah, these are the operations which generally perform. We scale the data and we find the best hyperparameter. So ultimately what we get is we search the highest hyperparameter using fitting and getting the best estimator, and then we basically use the best model to predict. Actually I should have trained it again. Yeah, this is the issue. Yes, model dot train on extreme. Okay, that's model dot fit. So yeah, this thing has been fitted here. This has given me the best model. I don't know if this best model has been with this check. If I use this here, what happens to the loss? Okay, it remains the same only. So I don't think so this line is needed. Or wait, let's undo. dot train. Okay, so I think this model has already been trained. That's good. So what basically we do is we basically take another model. Say generally what we do is we define the model here. Model is equals to linear regression, and what we do is then we basically pass this whole value here as it is. Okay, the best estimator value here, and then we use model dot train on its train. Let's print this data estimator. Let's just use it here. Okay, so best estimator, I think that should be 2 and 2 only, that's why it's not given. Oh, sorry, it should, we should not use this, we should just use this model dot fit, sorry, my bad, x train dot comma y train. So yeah, I think this error is still the same, the loss is still the same, everything is same. So I think this is already the best model which we have used. So yeah, we move away from linear regression. So any doubts till now? That is all about using basic functions of Python to implement linear regression. Nothing. Train and fit, they are the same terminologies. Train, that was the wrong function I used. I should have used fit. I used it wrong. Any other doubts? We are implementing linear regression model on our data. The model which was taught in week 2 or week 3 to you. Week 3 I think. Assignments were there. Week 3 or week 4 I don't know. So we are implementing that model on using these features. And this is target. So yeah, this is how you implement linear regression. Okay. You know, very basics of linear regression. Now what we'll do is we will also implement logistic regression. Implementing logistic regression is a bit different because there you don't need to find the values, you also need to find the classes associated with it. Okay, so we will implement logistic regression from here. We also optimize, we also learn the hyperparameters, etc. etc. So yeah, let's do it. Implement logistic regression on iris framework. So this will implement. So yeah, let me go one step at a time. These are all the basic libraries which we'll be using. Okay. And this is the data set. So it is basically iris data. load iris, and if I print it iris, so it has given me a lot of stuff like that. So what I'll do is I'll convert this data set to pandas data frame again. Okay, so we'll use structure like this. Okay, so as you can see, let us see the recommended plots. Okay, there are so many recommended plots because it's generating the plots randomly. And the problem with randomly generating plots is that most of the plots are not of any use to us. Okay, so as you can see here, this is the sepal length. What are the features here? So basically, iris flower has 3 types of flowers, Virginica, blah blah blah. Here 3 classes are there. You can just go to Google and search it. So it has petal and sepal. So petal is basically the colored part, and sepal is the green part below the petal. So the length of petal and sepal determine which class is which. So as you can see here, petal width is 0.2 for class 0, but it is quite high for class 2. So I think petal width should be the determining factor to determine whether it's Virginica, blah blah blah, what class. Like there are 3 classes here. Target has 3 classes, 1, 0, 1 and 2. So that's how you can determine. And sepal width, so length and width, they are almost similar. So I don't think so they will create any type of distinction. So what we'll do is target value is not calculated, it's the class of the flower. What kind of flower is it? Some kind of flower 1 means some kind of flower, 2 means some kind of flower. Yes, target is a categorical variable. That's why we're using logistic regression here. Yeah, so that's all we do on this. So yeah, let's split it into train and test. We split the data into train and test. Then we apply the scalar transformation again. So in logistic regression, since we are creating a boundary compared to linear regression, so scalar transformation is must in logistic regression. Okay. So as you can see here, it is showing, it is taking some iterations to run the code. So it is telling for increase maximum iterations or better conversions. Okay, let's just predict and see the accuracy here. Accuracy is 100%. This means our model has fitted perfectly. Okay. So this might look like very difficult, like at once, but it's not that much daunting. If you just do it yourself, and you will find that it's quite easy to basically use this stuff to train a model. Okay. Yeah, it is a classification rewriting. Depends on task. For cancer detection, you don't want 1% error. For housing prediction, you can basically adjust to some $1,000 or something. Okay. So any doubts till now? Okay. So yeah, that's all about logistic regression. And but the thing is again here, hyperparameter tuning. So what you can do is you can just let me just do it. Okay. Tuning hyperparameters. Parameters of logistic regression. Okay. So logistic regression has these four parameters: C says, regularization, strength, penalty, L1, L2, lasso range, solver, live linear, saga, and iterations. These are iterations, so it will just run and it will take the best model. So it might take some time. Okay, so it is even warning. It is showing best hyperparameters are these only. Okay, so. Accuracy with best hyperparameters, where is it given? Accuracy with best hyperparameters is given here. Okay. So we get best hyperparameter C is equal to 100, max iteration is 100. Okay. So this is what we get. Now this is how we tweak the hyperparameters of logistic regression model. Okay. Any doubts till now? Okay. Yeah, so these are very basic steps of doing machine learning. Next week, what we'll do is next week we will start with CNN stuff, CNN etc. You have been taught. We'll see how CNNs are implemented, how we do it in Python, TensorFlow, PyTorch, etc. etc. Okay. So let's discuss the queries and assignments. So what week has been completed? Let's go to the assignments. I will just let me just upload this notebook. This is week 7, right? Week 7. CS. Okay. So till week 6 of last year we have discussed. This means we have to discuss week 6 of this year. Okay. I will paste the link here after the video. So this is the current week 6 assignment 6. Yes. Sorry? Yeah, these are assumptions only. You can assume infinite number of possibilities for values. This is just rough estimate. Okay, so based on your use case, you have to assume what values might your model fall into, and then you check whether which set of the values is relevant for you. Okay. This is week 6. We have discussed it last week. This is week 7 of last year. Okay. So what are primary motivations for using CNNs over traditional RNNs? ENNs. The answer is simple. CNNs can automatically learn relevant features and special structures in images. Pooling layer reduces special size. Okay, so yeah, that's it. Pooling layer reduces special size and provides invariance. No. Yeah, it is the example in match pooling. Yeah. So you have an image, okay? And if you reduce the resolution of that image, the image remains the same, right? I mean, a horse is there in the image. So listen to me. There is an image. There is a horse in the image. Okay, the image is say 4000 pixel image. You reduce the image to 512 pixels only. Whether the horse stays horse or it converts to some other animal. Okay, so this is translation. I'm telling you, this is translation invariance. So if you just keep on training your CNN on without translation invariance, it will not be able to identify when the image of smaller size comes in. Okay, so that's why we use translation invariance to make it. We use pooling to make the model translational invariant, so that it can identify. So these are like match pooling is there, min pooling is there, average pooling is there. These type of operations are there. Okay. So parameter sharing means sharing some weights across different regions of input. So serials follow this concept because we are using single kernel for whole image. We are not using different kernels for different parts of the image. We are using simple filter or kernel for whole image, which means across different regions of image. It reduces the number of parameters and makes the model learn specially invariant features. Which of the following statements describe the main purpose of transpose convolution edits? So, transpose convolution reduces the size of activation, no. It acts as agglomeration, no. Increases the size of feature map, improves stability, no, it's not. I mean, these two options are mostly correct, but basically transposing the convolution helps in upsampling, as you might have studied in videos. Yeah, it helps in put a task. These are very simple questions. 10 questions. Which of the correct description of significance of 1+1 convolution using inception module? So inception module, I told last doubt session, it reduces the dimension of feature maps from say 60 million to 12 million, something like that. It reduces computational cost. So yeah, this is the correct option. Vanishing gradient problem is that when the gradients are low, or they become diminished and the weights remain same. So this happens when networks are deep because we multiply gradients using chain rule. And if the gradients are say decimal 0.02, the second gradient is 0.04. This reduces the gradient to 10 raised to power -6 or -4. And then the value becomes small and the weights do not change. So this is the correct option. Difficult to propagate result. Which of the following explains how density architecture facilitates implicit deep supervision? Oscillator classifiers, they are not oscillator classifiers. Direct skip connections. DSCAP does not have direct skip connections. A concatenation of previous preceding feature maps at each layer. Yeah, these are the video-based answers, like you can watch the videos and write it. So you have a CNN 64, 64, 20, 16 filter, bias term, how many parameters does this layer contain? I don't think so this needs to be solved. This was taught in last class also. It is something plus something minus something formula type of thing. Okay, so yeah, these are the rest are very simple questions. I don't. If you have any doubts, just let me know. I'll discuss them. But they are very simple formula based questions. Do you have any doubts? Okay. So now coming to this assignment, week 7 of last year. Let's open assignment. Let's open solutions. What is the primary goal of semantic segmentation? Detection? No. Classification? No. Pixel-wise labeling of objects? Yes. That was question. Nothing says segmentation will label the objects pixel with by pixel. Which layer type is commonly used in decoder part of encoder-decoder? So, as discussed in last week, we use convolution transpose for upsampling and encoder-decoder. So, yeah, convolution transpose here is used in encoder-decoder architecture. Which hyperparameter optimization method leverages probabilistic models? Bayesian. Obviously, it's Bayesian. Grid search does not use any probabilistic model. Genetic algorithm, no. Random search, no. Bayesian optimization is the only algorithm that uses probabilistic models. In transfer learning for image classification, what does fine-tuning do? What does fine-tuning do? Trains only a few last layers of pre-trained model. Okay. I think this is a very simple assignment, right? Even I don't have to open this sheet. Okay, so yeah, let's go to the next question. When fine-tuning a multi-layer pre-trained model, what layer can be freezed if you want to maximize adaptation to new tasks? The starting layers can be freezed, the early layers, very few layers, because they basically capture generic features such as edges, etc., etc. They don't capture the holistic feature map of the object in the image. So those things are captured by output layers and middle layers. Which of the following hyperparameters are the hyperparameters to be tuned in training? I think all of them actually. Learning rate, yeah, you have to if there is a hyperparameter, you need to tune it, okay? There is like the parameter weights you don't need to tune because they are learned automatically. But whatever other hyperparameters are there, you need to tune them. Parameter weights means the kernel size, W1, W2, you do not need to tune. But how many Ws do you want? Whether you want to square the feature or not, like WX square or not. Okay. Your network seems to have bias. This means the network is not deep. We increase the depth. Or basically the network is not that much complicated. We increase the depth. Generalization removes overfitting, which means it goes towards the bias. So there is a line. This is overfitting. This is bias. You go from overfitting to bias, or bias to overfitting. Regularization takes you from here to here, somewhere around best fit. And increasing the depth takes you from here to here. So this is the best fit, where there is no bias and no overfitting. Okay. Variance reduction. Variance can be reduced. See, regularization reduces variance. Number of neurons, no, it increases variance because your network is already deep. That is, from bias part we have moved over towards this side. Okay. Git augmentation, yeah, it reduces variance, and dropout, it reduces variance. These are some of the concepts. Okay. So I don't know what, like it has been a long time since I read unit paper. So the correct answers are given in front of you. Okay, so you can just go through these answers. Sleep connections are basically used to basically incorporate features for using downsampling and upsampling operations of encoder-decoder architecture. So that is why we are using them. The authors, how did they deal with the small data set problem? I don't know. I think the augmentation part, where the augmentation part helps in dealing with small dataset problem. So rotation, scaling, switching, shifting, grafting, whatever there are, like multiple augmentations are there for images. So they basically help in data augmentation. So these are the 10 questions of week 7 assignment of last year. So any doubts in these questions? Okay. So yeah, coming these weeks, the concepts will become much easier, yet they will be in-depth analysis of those concepts will become difficult. So as it said, the advanced concepts are built on these basic concepts which we learned in previous weeks. That's what makes them simpler, but this doesn't mean the advanced concepts are simple. Okay. So yeah, any other thing you want to discuss? You don't need to understand the architecture. These architectures were proposed very back in the day. If you are asking me this AlexNet architecture, why was it proposed? I cannot tell. Those people experimented with this thing and they came up with this architecture. So as you can see, this pooling basically creates translation invariance. Okay, this fully connected layers convert it to some probabilistic distribution. Okay, and these are the convolution operations which are performed on this. Okay, so there could have been 4 convolutions here, but they chose 3 because they found it convenient. So any architecture you see that may improve on some previous architecture, okay, but that doesn't mean that architecture is the best architecture. I mean, you don't need to know the thinking of the paper writers. Okay, they found that architecture best, that's why they have proposed it, otherwise it would have been something else. Sorry? So, I mean, I'm not getting the question. Yeah. There's no constraint like max pooling. See, max pooling can be, they have applied this max pooling operation taking 3 pixels at a time, so like 9 pixels at a time. Okay, they could have used 2 pixels, 4 pixels at a time. So the greater the size of this pool matrix, the smaller the image becomes. Okay, because you're taking greater number of pixels. So if I take your image is 4096 into 4096 and I take 4096 into 4096 max pooling, it will become a dot. Okay, so that's why it is not suggested to basically reduce the image to that much. So what you do is you make the image 1/3, half, like that. You don't just squint the image to a small dot. You make it in something in between. So that is all hyperparameter. These all things are hyperparameter only. These are computed while training only. Okay. Anything else? Batch gradient descent is you take whole data set, you pass the whole data set at once, then you compute the loss, you sum it, and then you backpropagate. Okay. So taking whole data set and passing it at once requires a lot of memory. So what can be the other option? Other option can be you take one data point at one point. But then what happens is you take some data point and you basically compute gradient as per that data point only, it creates problem because that data point causes variance. So your gradient fluctuates a lot. So what you do is you take mini batches. Okay. So yeah, that is all about this week's stuff. Any other doubts you want to discuss? Anything you guys want to discuss? What is the date today? So, okay. Okay, so anything you guys want to discuss, or let me just show you some this interesting blogs. Okay, so you guys have read neural networks, right? Studying neural networks. So let me show you TensorFlow playground. It was a very interesting concept. So consider you take your data to be linearly separable. This is a classification task. Okay. A classification task, and your data is linearly separable already. Okay, so what you do is ratio of training data to test data is 50%. Let's make it 60%, 70%, 80%, 90%. So now trained data is very high, or if I reduce to this, see, trained data is very low. Okay. If I increase noise, if I increase batch size, the algorithm improves. Okay. So yeah, what happens is, let me show you. You have some x1 feature, you take some x2 feature. x1 means this plane, x2 means this plane. Okay. If I increase this thing, another feature here. So x1, x2 can separate this data easily. This x3 feature cannot separate it, but this feature can separate it. Okay, x1, x2, this. Okay, so let me remove it. When we take 4 neurons, okay, if I increase neurons, it will increase the complication. If I decrease neurons, they make it very simple. Okay, so these are 4 neurons which you have done. If we reduce the number of hidden layers, the model becomes very simple. If we increase the number of hidden layers, the model becomes very difficult. Now we increase. We have not trained the model yet. Okay. Now we'll start the training. See how the image is converging to a final line. Seeing it, right? This is learning rate. This is the activation that's used sigmoid. Sigmoid takes a lot of time to converge than tanh. It might not even converge. See, what happens is, someone might have told you sigmoid, what is the problem with sigmoid layer? Sigmoid layer basically reduces the loss to very small numbers. So this is the activation now that's converted to use ReRun. So that's why ReRun and tanh are preferred over sigmoid. Okay. Very perfect line. Now what happens is, let me increase some noise here. Let me add some noise and then let's see. So see what perfect model. If had it been overlapped with this thing, this noise points, the problem would be it would have see it has started to overfit. This is taking these data points into itself, and it has started to overfit. Because of these noise points only, the axis has shifted from here. This plane of classification has shifted from here to here. Okay. So that is why training for a lot of number of data points basically increases the noise. So see, these are the perfectly separable apart from these 3-4 data points. There can be noise. See, initially it's good. If I stop it here, it's very good. Then apart from these points which are here, the plane is perfect. But if I keep on training, the plane will shift. The number of data points will increase. Sorry, this will increase. This classification shift here. Okay, the classification will shift, and if I just show test data as well. Am I audible? So see, over time it will start to overfit. It will take some time, but it will overfit. Axis will shift to this something like, but since the points are in between, it makes it difficult to overfit. So if I reduce to 5 points, and then you will see it overfitting. So this is the perfectly fit line. So this is the playground where you can practice all the stuff you want. Then let me reduce the number of hidden layers. The number of hidden layers are a lot. Now we have 3 hidden layers. We increase the neurons, we increase the neurons, we decrease the neurons, and then let's see. So since the data is simple, this is very simple. Okay. So now let's go to some data like this. This has 4 planes, right? So initially, if we use this is a perfect plane, this is a perfect plane, but it will not be able to separate until we use this feature. Okay, so let's see. Yeah, 2D plane only. The line becomes plane. Okay. Yeah. So see, these 2 features are insufficient at separating the boundary. So we include this feature as well, and then we start. See, perfect fit. Okay. If we increase the noise here, and then we do, the noise will cause the axis to shift from center to, like, it creates deviations. See, the noise has shifted this axis. It has these planes have shifted due to noise. So what we do, let's remove the noise for now. Let's increase the batch size. That way the learning will increase faster. See, beauty of this whole chart. So we have seen how we should also include this feature as well. So we have seen how including these features help in basically, let me reduce. Yeah. So underfitting means the line is not clear. See, I will show you. Let me just place here. I will decrease the model. Okay, I'll delete this layer. Now let's see. This is a very basic model, right? This is underfitting model. The model is not fit yet. Overfitting I've shown you, it fits to the noise as well. Okay? So now let's increase this feature and this features. Okay? And let's add this feature as well. And then let's see. So see, adding this feature has created some different type of architecture. This feature creates some quite close. It is quite close, but this feature has basically created a different type of boundary, which is not required. See, but it's still, over time it is fitting. Over time it has started to fit, but this feature makes it unnecessarily hard to train. So we remove this feature and we train it like this. Now this has become perfect. So as you can see, these are lines. These are lines because the model is very small. Okay, these lines are not converted to some circle type of thing. So what we do is increase number of hidden layers. Say, and then let's see. Now the lines will start becoming smooth curves. Smoother curves. Okay, we have increased the complexity. The function has increased complexity. Now these lines have become smoother curves. Okay. Yeah. Depends, yeah. Generally it is an overfit because test loss is generally lesser than train loss. Okay. So that is generally an overfit case. Otherwise, if the test loss is less and train loss is more, then it is a bias. Like it is bias from start only. Because if train loss is more, you won't start testing the model. The model is not very good. So now let's try this on spiral data. So spiral data, I will take the same type of framework, and it will take some time. It will take a lot of time actually. So see, it has started to create multiple boundaries, and over time these boundaries will shift in circular manner. Okay, see how their boundaries are shifting. Looks beautiful. So as we know, the spiral data is some sort of sinusoidal data record thing. So we add some sinusoidal waves here, and then we train it, and then you will see the spiral lines will fit much faster. See, the sinusoidal nature basically helps in creating a better sort of architecture, better sort of plane. Okay, so let's increase some more complexity. Let's add this feature as well and then see how better does it go. So as you can see, test loss is compared much higher than train loss, but at one time it will just see now the test loss, train loss is also increased. So I mean adding this feature hasn't done anything. Let's add these features as well and see. So this is what feature engineering is all about. You just see, wow, beautiful. It's like a heart is beating in my eyes now. Yeah, so say train loss and test loss, they are fluctuating between 0.01 and 0.04. Okay, so yeah, I think this will be the best fit curve. So you can just use this playground to learn more about architectures. I will paste this link here. You can Google search it and use it. Okay. So yeah, this is the playground, which is an interactive way to learn about this stuff. And yeah, then that would be all. Anything else you want to discuss on this playground or anything? Just Google search it. Yeah, it is open to everyone. TensorFlow Playground.org. TensorFlow was created by Google, PyTorch was created by Facebook. That's all. They perform the same thing. Okay. So if you see Google has GPUs, TPUs. So Google produces this tensor processing units. They are not sold to anyone else. Because the first of all, the TensorFlow package is compatible with those TPUs. PyTorch might not be good. And second thing is, since Google owns the terminology TensorFlow, so it uses the tensor processing unit type of thing. So this will be quite evident why Google owns the rights. Everything in this AI world is basically controlled by these giants only: Google, Meta, NVIDIA, OpenAI, Microsoft as well. So yeah, that would be all. Anything else you want to discuss? Cool then. Let's interact. everything, whatever new model will come now, it will create some sort of hype. And the other thing is the benchmarks, the data sets on which ChatGPT, GPT-4o were proposed to be beating the benchmark, beating the state-of-the-art model. DeepSeek seems to have beaten those benchmarks. So that is why they have, like, there's a huge buzz in this AI industry that DeepSeek might overtake ChatGPT and OpenAI. But the other problem with that is, yeah. Yeah, I mean that is the issue. Now you don't know. You haven't seen that they are saying the token cost is low. Okay, that might, because they want to disrupt that AI industry in USA. They might be losing some money by not asking people to pay more for tokens. Okay, they might be losing that money, but who knows? Like token cost. But yeah, attention approach is novel one, but reinforcement learning, I mean, GPT-4 has used that to train the model. Okay, so it's not very thing like it's just what the people in the academia industry feel, that it's just a hype. Because once you start using it, you will find it. You will find that the reasoning model is particularly good, but the accusations have also been made that it uses an API to ChatGPT or GPT-4o in backend to basically get the response from that model and serve that response to you. So the purpose for creating DeepSeek, as per some, not just filter data, yeah, the data that has been used to train the model, that is also, but in providing responses as well. It uses some GPT-4o API in the backend. Okay. The other thing is that DeepSeek was created by China, or they are saying that they were not provided GPUs by USA, so they used less number of GPUs to train it. But who knows? Who knows that like these allegations can be easily made just to prove the point that now you don't need GPUs to train the model, so you don't need NVIDIA and GPUs. You don't need to buy GPUs from NVIDIA. You can just simply take smaller GPUs and train the model. But that is like, there's no proof for that. Whatever you can claim, you can claim. I can claim I trained the model on 5 GB data and 5 GB GPU, but I won't give you the training data and I won't give you the weights and the training script to train the model. You have to figure it out on your own self. Okay. They have provided a trained weights, but those weights are just for inference purposes. They are not, and you cannot deploy. The weights are very low, 60 billion or something. As a student, nobody can use that. So that's another thing. So these models will just keep on coming day by day, and we cannot do anything. Like you cannot, like this DeepSeek had this thing disrupted USA market, but now nobody cares in USA about DeepSeek. It was just a 2-3 days thing, a week or two. After that, everything went to the shelf, and now the whole country is working as if DeepSeek never happened. And I don't know, like people would be using DeepSeek. I use all three models, I use Perplexity, I use DeepSeek, I use ChatGPT, and personally I don't find any difference. Like, you can use whatever you want, it's just prompting. For tasks, simple tasks such as what we do, it doesn't matter to us. Solving mathematical problems, DeepSeek also fails on complicated mathematical problems, ChatGPT also fails. So overall, it's just, you say, Yippee noodles versus Maggi noodles, whatever suits your taste. So yeah, that's all. If someday Rin comes and says tide is not better, Rin is better, and tide comes and says Rin is not better, I am better, so you will not change your preferences. At your home, you might be using Ariel detergent, so you will not just throw away Ariel detergent, you will start using Tide. So that all depends on your use case. Okay. I mean, if Tide says it's better, And next day, what makes you think that Rin will not better itself? It can. They have the power. They have the money. We are the people who just keep on debating, but these bigger people play a bigger game there. I mean, I should give it here only. Playground TensorFlow.org. Okay. Another thing is, say, like, there's a concept in share market trading that's shorting the stock. Okay, so you short some stock. What you do is you purchase the stock, sell the stock at higher price, which is like, say I short the stock. I'm saying, say Praveen is there. I'm telling Praveen, you can buy Nvidia stock from me. The Nvidia stock is, say, $542 per share, and in that way, I will sell that stock to Naveen at $452. Naveen is ready to buy that stock from me. Okay, but I will not give that stock to Naveen because the stock price is very high right now. But I know that price will go down. Okay, so in that case, what I'll do is I will launch DeepSeek, and I will propose some claims that DeepSeek was trained without using GPUs, and that will drive down Nvidia stock from $452 to $100. And then what I'll do is I will purchase that stock for $100, and then I'll give it to Praveen. Okay, Praveen thinks that stock was given to him at $452, means that I purchased it at before Praveen, but no, I purchased it after Praveen was provided that stock. So that is what shorting means. That is what China might have did. I mean, you have to basically show government when you purchase huge number of stocks beforehand. I mean, you do shorting, but what makes you say multiple agencies cannot do it? Multiple agencies can do it in small numbers. And ultimately, now Praveen is holding $452 stock, which is valued at $100 in market. I'm going home with $352 profit. So per stock. So that's how you can make money as well. I mean, but this is, sorry. Yeah, you have purchased for more money, and this is shorting, etc. You cannot do. We common people cannot do. These bureaucrats, these businessmen, they only can do. They know what will drive down the stock. Even you cannot purchase a stock without using these trader apps or stocks and trading platforms. But they can purchase the stock just by picking the phone. Okay, so they will tell your trader to sell this stock at $452. The trader will sell the stock to someone, virtual stock. The stock is not sold to that trader, the person owns that stock in the app, but that stock has not been sold by you, that app to you. Then it shorts the stock. It's completely illegal. It's a gray area, and that's again a conspiracy that China might have done this to basically drive down the media stocks and gain some money. But who knows? So yeah, this is DeepSeek versus OpenAI debate. My preference, I mean, I genuinely preferred this OpenAI because Sora, etc., video generation, a lot of stuff apart from the text data, which is very good in ChatGPT. Okay, the code generation part, the code running part, graph generation. So it helps me writing, it helps me creating PPTs, etc., etc. This DeepSeek cannot do. So I mean, in future it may save me my money. I'm paying premium for the ChatGPT. I mean, I just want something for free. I will get it. I mean, but right now I consider that $20 investment a month on ChatGPT better than using DeepSeek. That's my personal opinion. So yeah, anything else apart from this DeepSeek debate? I planned that way because the assignments this week were very simple, so it would have been finished in 30 minutes or so. So that's why I planned this whole thing for today. Next week we'll meet and see what we can. Let's discuss assignments, and then we will discuss how to implement CNNs and how to read images, etc., etc. I mean, you can do it yourself. Just open Google Colab and open Gemini search, type the prompt, and it will give you the code. Okay, I'm not doing anything different, I'm just doing the same thing, but I don't know, like, people might not be able to do it, that's how I'm doing it. So, yeah, anything else you want to ask? or shall we wind up? Cool. I think then let's wind up and let's meet next week. Next week I won't be here probably. I'll just send an email to NPTEL team to shift the session to Thursday probably, not Friday. I'm going to a conference, so I'll let you know. I'll just email and send on the session portal as well. So yeah, I think that would be all. Let's meet next week on Thursday or probably Friday. That depends. Till then, take care. Bye bye. Good night.